randomized. For example, here I have a schematic plot for a randomized experiment comparing two treatments. So we have a group of subjects randomly split into two treatment groups, right? Apply A and apply B. Because of this randomization of treatment ensures that different treatment groups are compatible on average. So we can compare apples to apples. So during the follow-up, we can collect their outcome and directly compare their outcome. And if you observe any differences in their outcome, it is due to the treatment, right, not by other confounding factors. So this is a major advantage of randomized experiment. It ensures the covariant balance, right? It ensures that different treatment groups are compatible in their observed and also unobserved covariates. We can eliminate confounding biases. While in practice, it's not always feasible to conduct a randomized experiment due to a lot of reasons. For example, financial reasons, logistic reasons, or ethical reasons. In those cases, observational studies are useful. And the objective of observational study is to elucidate cause and effect relationships. So here's a quote from William Corcoran back to 1965. However, we need to be extremely careful in using observational study for causal inference because of the confounding issue. Because we do not control over treatment assignment mechanism. Therefore, different treatment groups may differ systematically in their covariates, right? So this is a confounding fact. So if we observe any differences in their outcome between different treatment groups, it may be due to the treatment effect or the confounding effect, right? So this is the major limitation of observational studies in doing causal inference. And a lot of causal inference methods has been developed to adjust for the confounding when we use observational studies. And the paper used the potential outcomes framework. So here's a basic setup. We have X, that's a factor of pre-treatment covariates. Z is multi-value treatment variables. So we can take on value 1 to capital K. And we imagine that each subject has potential outcomes, YZ. That's potential outcome have the subject receive the treatment little z. And again, Z can be 1 to capital K. So these are mathematical constructs, right? Hypothetical construct, because in reality, for each subject, you can at most observe one of the potential outcomes. So observed Y corresponds to the potential outcome under the actualized treatment regime, okay, Y capital Z, and other potential outcomes are missing, right? So the causal inference problem fundamentally is a missing data problem. But using potential outcome is very useful because you can define what is the treatment effect very clearly. So for example, we can focus on average treatment effect comparing treatment Z to Z prime. So that's defined based on the average, the expectation of YZ minus YZ prime, right? Without any confounding issue. And also we can define the average effect on the treated. This is defined similarly. And it's very useful, the paper point out that for the multi-level treatment case, the average treatment effect Z prime may be different from a pairwise comparison because fundamentally they are looking for different population. One focus on the entire population, so that's ATE, right? And one look at just the pairs, the two treatment groups. Okay. So the fundamental problem in causal inference is that not all the potential outcomes are observable. Therefore, we require further assumptions to identify or estimate the causal estimate. And typical assumptions in the causal literature is the strong ignorability of treatment assignment. So it consists of two parts. One is no unmeasured confounding assumption. So the formulation is here, but the implication is that X should capture all the variables that related to the treatment assignment Z and outcome Y. So it should capture all the common causes of Z and Y. Then condition on Z, condition on X, the treatment randomization as good as randomization. Okay, so then we can have some kind of conditional randomized experiment for observational study. And then the second assumption is positivity or overlap assumption. So it requires for each subject, there is a positive probability of receiving either all the treatment. For example, Z can be 1 to capital K, and the other conditional probability should be greater than 0. Okay, and this conditional probability, the vector of the conditional probabilities are called the generalized propensity score if we focus on multi-level treatments. Okay, and under this assumption, people show that the treatment effect is identifiable and estimable based on observed data. So you don't require potential outcomes to be observed for everybody. Okay. So under this result, then a lot of causal inference methods have been proposed to remove the confounding biases by adjusting for covariant imbalance between different treatment groups. And there are two popular and very intuitive approaches, including matching and weighting. And these are the two methods focused on in the paper. The paper talked about like one method from each category of the approach here, matching and weighting. So I'm gonna illustrate how these methods evolves, okay? So matching idea is quite intuitive. And the first idea is matching based on covariate, right? Because it can directly target for the covariate balance between different treatment groups. But there's some problem. For example, you can imagine that as soon as you increase the number of matching variables, then no one is close to anyone else, right? And then this can lead to discrepancy in the matching variables and also residual confounding biases. So here we have a very naive plot, so you probably cannot read the words here, but the idea is you can see the two people are matched together. They have same values in age and their gender, but there are some still discrepancy in education and physical activity. Okay, so this is due to the matching discrepancy. Okay, so you can imagine if we have 100 covariates in X, then no one is close to anyone else, right? So match on 100 dimensional X, you will have like residual confounding biases. And the idea of vector-based kernel weighting is to do dimension reduction in matching procedure. So matching based on covariate itself may suffer from curse of dimensionality, and we first need to do dimension reduction. And the idea here is to use balancing score as a way to do dimension reduction. And Imbens 2000 to show that the vector of generalized propensity score can serve as a balancing score. This is very powerful result in the sense that if we balance on the vector of GPS, the generalized propensity scores, it will guarantee that we can balance X on average. So what it does is try to block the pathway from X to V, and therefore you can remove the confounding effect from X, okay? And you can imagine, right? So X is 100 dimensional, but if we say have T is three treatments, then you only need to match based on the two dimension generalized propensity score. Okay, so this is very powerful result in dimension reduction. So the vector-based kernel weighting is the same idea. Okay, so we first do matching based on the generalized propensity score. Okay, say we have M matching unit, but the vector-based kernel weighting do additional things. So it assigns the kernel weights to each matched unit based on the distance between generalized propensity scores and assign different weight to the matching unit. So the idea is try to smooth the imputation and therefore improve the efficiency of the matching estimator. Okay, so that summarizes the idea, the basic idea of vector-based kernel weighting idea. And another popular covariate balancing strategy is weighting. And everybody knows inverse probability weighting, right? So we first try to predict the propensity score and create the inverse of it that becomes the inverse probability weight. And we know that the weighted sample actually should have the randomization or treatment because it creates a pseudo population where there's no confounding, right? So that's the idea. But there are some problems associated with the inverse probability weighting because it first tries to predict the propensity score and creates the weight by the inverse of it, right? And it cannot guarantee balanced X for every sample, and also it suffers from instability. So you can imagine that some propensity score estimate is very close to zero, then the inverse probability weight will be very large, right? So that's the instability. And entropy balancing is proposed to stabilize the weight, okay? Or I actually call this calibration weighting because this is a more general class. It includes the entropy balancing as a special example. So calibration weighting learns the weight directly. Instead of estimating the propensity score first and doing inverse of it to create the weight, it tries to learn the weight directly, where the target is to enforce the covariate distribution to be balanced between different treatment groups. This is more targeted learning, right? So let's focus on the average treatment effect for illustration. And the idea here is we want to assign weight to everybody in the sample, right? And we try to calibrate the covariate distribution from each treatment group to the overall sample. And therefore, the different treatment groups will have clear balance, right? And for illustration, let's look at the treatment Z group, and then we assign the weight to each one in the group Z, okay? And here, the constraint means after calibration weighting, the weight and mean of X from the treatment Z group is the same as the overall sample mean X bar, okay? And we can do this for each group, and therefore each group will have the covariate balance, okay? And then here X can be the first moment of the covariate or the second order or the higher order moments, okay? But there are different weight solutions that satisfy the constraint, right? The idea is how we're gonna have a unique weight solution. And the calibration weighting try to minimize the distance of the calibration weight, the new weight, and the original weight, okay? Subject to the constraint, the calibration constraint. And H is some distance function between the calibration weight and original weight, okay? So H can be flexible. For example, we can choose Euclidean distance, but we can also choose negative entropy. So if we choose H to be negative entropy, it becomes the entropy balancing approach, okay? And the advantage of entropy balancing is that if we minimize this criteria, that means we maximize the entropy of the weight solution, right? It ensures the empirical distribution of the calibration weight is not far away from the uniform weight, and therefore it controls the variability of the final weight, okay? So that's the advantage of entropy balancing, and it has been performed very good, very well compared to other approaches in terms of bias and the efficiency in binary treatment setting. And then here is a gap stated in the paper. So the key limitation is that we do not have literature or guidance on the use of entropy balance in the categorical treatment setting. And the paper tried to fill in this gap. And the approach taken in the paper is conducting very extensive simulation study. By extensive, I mean exhaustive. Here, the goal is to compare the finite sample performance of vector-based kernel weighting and entropy balancing. And here, the paper takes the factorial design for the simulation design. So it compares 7 functional forms of treatment assignment, 3 sampling distribution, 5 coefficient sets, and 2 treatment effects. So all the combinations amount to 210 simulations. So this is a lot. In evaluation metrics is biases, efficiency, also coverage probabilities. And here are the finding and some recommendations from the simulation study. So overall, entropy balancing have better bias and also mean square error than vector-based kernel weighting when it because it may fail to converge. And then here it shows the probability of a failure of convergence, and then the axis is some imbalance measure of the covariance between different treatment groups. Okay, and the imbalance is measured by the absolute value of standardized mean difference of the prognosis score. So because we have a large number of covariates, so we need to have some summary. And the summary is prognosis score. Okay, and then so the absolute value of the standardized mean difference is just a measure how imbalanced the covariates are between different treatment groups. And then you can see as the imbalance increases, the probability of failure of non-convergence also increases. Okay, so that's the some limitation for entropy balancing, and this can be an issue in multi-treatment case, because in multi-level treatment case, you can imagine that the imbalance may be an issue. right? And another issue for entropy balancing is that it has a conservative coverage probability for confidence intervals. Okay, so sometimes the coverage probability can reach to 1. So this is quite conservative. And from this observation, the paper recommend that first, one can implement entropy balancing. If it fails, then one can do vector-based kernel weighting. Okay, so that's a recommendation. But my question is, what is the performance of this recommended estimator? It actually is a combination, right? It combines the entropy balance and the vector-based kernel weighting. And what is this recommended estimator performs in terms of bias, efficiency, and coverage probabilities? Maybe you need to include this as a competitor in the simulation study as well to assess whether the recommendation is good or not. And secondly, in practice, you do not know variance, right? So although the entropy balance may have better real mean square error compared to vector-based kernel weighting, but you don't know the true variance. You need to calculate the variance and then construct confidence intervals. So if the entropy balance is conservative in inference procedure, then it may lose the efficiency, right, compared to the vector-based kernel weighting. So we also need to see the weight of the confidence interval, compare the weight of the confidence interval as well. But in the end, I wonder why the non-convergence happens and why it is conservative, right? So here's my 2 cents. So what calibration weight or the entropy balance does is the following. Calibration weighting actually assume a parametric model for the weight itself. Although it is proposed based on some optimization problem subject to constraint, it is nothing different compared to the IPW approach. It also imposes a parametric model for the propensity score. Instead of imposing it directly for the propensity score, it imposed the parametric model for the weight, right? So if we look at the dual problem of the optimization, we apply Lagrange multiplier and we can find the weight solution explicitly here, right? And here eta is a link function, so it is imposing a parametric model for the weight. Okay, and the lambda z here is some Lagrange multiplier, but you can also view lambda z here is some the parameters in the parametric model. Okay, and then instead of using MLE, the calibration use the covariant balance constraint to solve for the model parameters. Okay, so this can be viewed as like parametric model and impose estimating equations to estimate the model parameters. If we view the problem in this way, then the calibration weighting estimator for the potential outcome means, or similarly the ATE, the average treatment effect, is essentially a Z estimator or M estimator. So by stacking the average treatment effect estimation and the calibration weight, okay, so estimating equation together, right? So the ATE estimator is just to solve the system of estimating equations, okay? So the consistent variance estimation follows immediately, right, from the literature for Z and M estimators. So this might improve the coverage properties of the confidence interval from the entropy balancing. Also, this perspective offers possible solutions to solving the non-convergence issue, because when there's no weight solution, right? So that means the estimating equation doesn't give you a unique solution, or there's no solution at all. But from the estimating estimating equation literature, people know how to solve this problem, right? We can add the regularization to the estimating equation, and this facilitates selecting important constraints for calibration among like a large number of constraints, right? Or soften the exact calibration constraint, okay? So adding regularization may help to resolve this non-convergence issue. And we think that in vector-based kernel weighting, we use dimension reduction, right, to reduce the dimension of the matching variable from X to the number of the GPS, right? And why not we use similar ideas in entropy balance? So dimension reduction can also improve the convergence of the entropy balancing algorithm by reducing the dimension of the calibration constraint. Because we see the role of generalized propensity score is balancing score, right? It can reduce the dimension of the calibration constraint. So similar to the vector-based kernel weighting, entropy balancing can also directly calibrate the generalized propensity score instead of the original covariate. Okay, this can resolve the non-convergence issue because we effectively reduce the dimension. Okay, and there's another role of prognosis score. Prognosis score is actually another balancing score. Okay, the paper used prognosis scores to signal when the entropy balance may fail to converge. But prognosis score is also a balancing score. So instead of calibrating X directly, we can also calibrate the T vector of prognosis scores. So one from each treatment group. So what it does is try to block this pathway from the confounders to Y, and therefore we can remove the confounding effect. Okay. And then the idea is why not we combine the generalized propensity score and prognosis score in calibration set, right? If T is small, we can combine the generalized propensity score and the prognosis score. So T minus 1 plus T is still not large enough, right? So adding, so we can calibrate both the generalized propensity score and prognosis score. And what we find is that adding the prognosis score in the calibration set actually can improve the efficiency and the robustness. Because in practice, you don't know the generalized propensity score or prognosis score, right? You need to come up with a model for that. If model is misspecified, so if we calibrate either the generalized propensity score or prognosis score, you have single chance to be correct. But if we calibrate both, then the idea is you can have a double robustness, right? If either the propensity score is correct, you can block this pathway. If the model for prognosis score is correct, you can block this pathway, right? So you can achieve double robustness, then you can still have consistency. Okay, so this is the idea of the double score calibration. And it turns out that it is advantageous to combine the use of models for propensity score and the prognosis score. So more specifically, it is possible to consistently estimate the causal estimate if either of these functions is modeled correctly. So this property is referred to double robustness. And the causal inference literature has a lot of work devoted to double robust estimators. So for example, the augmented inverse periodic treatment weighting estimator or the augmented calibration weighting estimator, they achieve double robustness. Okay, so you have two arms to be strong. And muscle mean can be very flexible in the sense that we can be very flexible in choosing models for the propensity score and also for the prognosis score. We can use semi-parametric, non-parametric, or even machine learning approaches for the two scores. For example, random forest, generalized additive models, kernel regression, and methods of sieves. So you worry that if we use very flexible models for the propensity score and the prognosis scores, we may not get the inference result, right? But the double robust estimator have the advantage is that we can have very relaxed conditions for the convergence rate for the nuisance parameter estimate. And in the end, the AAPW estimator or the ACW estimator can still return the root and consistency and a single Tartian normality. So in the sense that you can still construct confidence interval and also control the type 1 error and construct the confidence interval, so on and so forth. Okay, so the variance can be estimated also by bootstrap. Okay, so the implication is in practice, it can be very simple, the implementation. And it can also achieve the semi-parametric efficiency bound. So in the sense that the double robust estimators is the best, okay, in the efficiency consideration. So here, the final plot is the comparison between ACW and the CW estimator for another context. So this is some plots extracted from my own paper, but I just want to show you that ACW can be very good compared to the CW estimator. So you can see the CW estimator has very large bar of the variance, but the ECW estimator is much efficient, right, compared to the CW estimator. So the ECW estimator and the robust approaches, I think it should be recommended in practice. With that, I'm gonna thank you for your attention, and this is a really good paper and a good study. I really look forward to seeing more good work coming out from the authors. Thank you.
Very high order models, but
Yeah, I mean, my guess is if that's true, then in your nonlinear data generating processes, you find that the entropy balance is not doing as well if you just match the first order limits.
okay,
Because you need the whole covariances and everything to match, and the data generating process is nonlinear in your outcomes.
okay, thanks.
This question might reveal my ignorance on the subject, but I'll ask. This is also kind of a question for Shu. So, it sounds like you guys, like there's less variance around the entry balancing estimator. Shu suggested like part of the, I think if I understood correctly, part of the reason Shu suggested doing the semi-parametric stuff is because you get nice like asymptotic results about the variance. Wouldn't you be able to get those same kind of results though for like constrained maximum likelihood with this setting?
I'm not sure I get your question right.
So I think like one of Shu's suggestions was like kind of pushing to say like, okay, why are you getting like less variance on your prediction?
Mhm.
And I think her suggestion was, oh, like, you know, it would be easy to prove something about that if you use the semi-parametric estimator because there's these results in the literature about it. I guess what I'm wondering is, it seems pretty obvious that there should be results about like constrained maximum likelihood, which is what you guys are doing as well. Because I think you guys are constrained likelihood to estimate this. Like, I guess it's partially a question for Shu, but also a question for you guys. But hey, like, have you considered looking, you know, that kind of like that?
Okay, I'll let you to take it first.
Yeah, I think I can respond to the previous question. So because of temperature weighting, yeah, indeed, only calculate the first order moment, but the suggestion is like incorporate the prognosis force, then it can
Then it will balance everything.
yeah. So I think that will
I think the augmented one is much better.
yes. And then the second question is for the entry balance, whether it can achieve the same energy efficiency point.
Yeah.
In some cases it can. In some cases it cannot. For example, if the true effect function is a linear in X, and if the conversion weighting approach already balances the first order movement, then it achieves the efficiency because it already controls the part.
Yeah, for the related reasons related to this question, yes, sir. Yeah,
Yeah. In general, it not.
got you. Because of the higher order.
Yes. So that's why you can see for the augmented conversion weighting, it can improve the conversion weighting and sample efficiency.
But something,